And this is charged, positively charged, of course, so you deprotonate here, which turns this into a single bond, and the bond of this carbon with this oxygen to a double bond. Again, a typical switch over of the two OHs. In other words, it's equivalent to this OH, like an alcohol, displacing bromide by an SN2. But mechanistically, it actually goes by attack here. I won't test for those mechanisms, but just to fill you in. And at that stage, this is such a good leaving group that bromide anion attacks additional elimination, and that makes the ACL halide. So OH turns into a good leaving group, OPBr2, and it's kicked out by bromide. And the reason that you need this in order for this mechanism to work, and or rather in order for the mechanism that we discussed in the halogenation of aldehydes and ketones to operate, is because you're activating the carbonyl function now to enol formation. Turns out carboxylic acid carbonyl is too happy, relaxed, to generate the enol spontaneously, or to put it differently, the keto-enol equilibrium is really terrible. So in order to make it accessible, you have to turn this into an intermediate ACL bromide. And at that stage, pKa of this guy is about 16, so this is now quite acidic because this carbonyl is now really pulling. With acid, you turn the carbonyl, the keto form, into the enol. So at this stage, we're completely analogous to aldehyde and ketone halogenation. Remember, that went through, with acid catalysis, through the enol formation. The enol is then halogenated, and that's the same thing here. So once we have the enol, we do the bromination, it's a weird enol, obviously, because it's got a bromine hanging off here, but it's still an enol. So it's an electron-rich double bond. Bromine attacks. You make, attacks at this carbon. You make the plus charge here, which is nothing else but a hydroxycarbocation, which is nothing else but a protonated carbonyl, and so the proton falls off, and that's your product. Okay? So these two steps are analogous to the halogenation of aldehydes and ketones. So that now you can understand why you need the phosphorus to make PBr3, because the PBr3 turns a little bit of the carboxylic acid into the ACL halide, and that enolizes and then gets brominated. And then at this stage, this guy reacts with starting carboxylic acid by a mechanism where the ACL halide, like any ACL halide, reacts with the carboxylic acid to make an intermediate anhydride. And there's a chapter integration problem that I'd like you to work through. So the integration problems are explained. They tell you how things work. There is a disproportionation or comproportionation, depending on your point of view, where one bromine trades places, or the bromine here is transferred to the other carboxylic acid. And so what you get, because the driving force is that this is now a really unhappy carbonyl function, because not only does it have a bromine on the carbonyl, but another bromine here also pulling. They're all pulling. So it stabilizes itself by essentially transferring the bromine to the other carboxylic acid. And that makes the product, plus this guy, which then just simply re-enters the cycle. That's where the catalysis comes in. Okay? So all you need is a pinch of PBr3 to make a small amount of this, and that then turns over by picking up the unreacted carboxylic acid at this stage, regenerating that, going through the cycle again, eventually turns over all carboxylic acid to the product. So overall, in terms of vocabulary, it's a variant on the acid-catalyzed halogenation of aldehydes and ketones, but don't forget that you need a little bit of phosphorus, and it only works for bromine, so that's how you make bromocarboxylic acids. So to conclude, we've been talking about these carboxylic acid derivatives. We've learned how to make them poorly, really, except for this guy. We learned good methods using inorganic reagents, SOCl2, PBr3, and the like, to make the ACL halide. This turns out to be the hardest carboxylic acid derivative. We learned about making carboxylic anhydrides, in which instead of X, we have a carboxylate, and I arbitrarily picked the right half of this molecule as the carboxylate part. Of course, you could have picked the left one. And then we can replace OH by OR. This was done by a pinch of sulfuric acid from the component pieces, carboxylic acid plus alcohol. And then we also learned about making amides poorly by blasting carboxylic acids with amines. The problem there being that you get ammonium carboxylates. But in all these cases, the crucial feature is nucleophilic substitution occurs by additional elimination. So if you call all of these functions to the right of the ACL group L, because they're potential leaving groups, nucleophile comes in, kicks out the electron pair under acid catalysis, or with the inorganic reagents such as thionyl chloride, PBr3, PCl5, that would be E+. They all attack on oxygen, or in this mechanism, it's another carbonyl function. Electrophiles always attack on oxygen, at least initially. Okay? And if it leads to product, that's a good way to go. Nucleophiles attack here, and when the nucleophile is attacked, this becomes a tetrahedral sp3 hybridized carbon, and so at some stage the electron pair kicks in and kicks out the leaving group to make it leave. So let's talk about these derivatives that we've already talked about, but now we talk about them in an organized manner and how they relate to each other. So here again, we got this ACL group with a potential leaving group here, all the potential leaving groups, and OH is a bad leaving group. These are all better leaving groups. Particularly for those that are normally bad, you can make them leave by protonation. All of those can undergo nucleophilic addition elimination, both acid and base catalyzed. Remember, with carboxylic acid, base was out, basically, so to speak, because the carboxylic acid is acidic, so it gets deprotonated. So these are much better derivatives to handle. And so generically, again, here's the generic nucleophilic addition elimination. If you come in with neutral nucleophile, you can attack, pick out the electron pair, get O-. O- comes back in, kicks out the leaving group. If this is done under acid catalysis, as long as that nucleophile is not too basic, then you protonate here, you spiffy up the carbonyl function in its reactivity, and then the nucleophile attacks, and you go into a mechanism similar to this. It's all a matter of when and where the proton is and comes up. Under acid catalyzed conditions, typically you protonate the oxygen, and then you shuttle the electron pairs. Under base catalyzed conditions, this would be deprotonated first, so this would be a nucleophilic, ideally a negatively charged nucleophile. That's really visually the simplest thing, because Nu- comes in, makes O-, and then the O- kicks back in and kicks out L, and you're there. So it's literally in and out kind of mechanism. So let's compare the reactivity of these, and I really basically already said this, but I'm now organizing this in one section to repeat everything I said before last Tuesday and earlier today. The most reactive ones are the ACL halides. because the halogens are furthest to the right, the strongest polars and the like. The next ones are the carboxylates, so now we're moving from halogen to oxygen, less electronegative, but this one is still more electronegative than this oxygen because it's got another carbonyl hanging off. And it's a carboxylate as a leaving group. These two are actually sort of comparable. This one is super hot, this one is hot. Then we tranquilize considerably when we go to esters, and finally the amides are the most stable ones. Okay? What this means is that left is most reactive, right is least reactive, left is least stable, right is most stable, meaning that any of the L groups that I've depicted here to the right of any entry in this row will displace the L group in the entry, meaning X can be displaced by carboxylate, alkoxide, or alcohol, and amine. Okay? And the anhydride, this L, this carboxylate, can be displaced by alkoxide and amine, or alcohol and amine, but not by halide. So you can't turn this into that, but you can turn this into that or that. Okay? This one is you can turn this one into that, but not into that or that. And finally, this guy is just stuck. Okay? This is the most stable, and you can't turn this directly into any of the precursors. That's the hierarchy. Okay? So the left guys can give rise to whatever is to their right. Okay, let me give you a feel for how this works out in reality. Just hydrolysis of all these guys. If you take an acyl halide, acyl bromide, or acyl chloride, very quickly, in the presence of water, you get hydrolysis. Okay? That hydrolysis occurs with moisture in the air. Okay? In fact, when you buy an acyl halide, it comes as a powder in a nice bottle and stuff, and you open the bottle, as you open it, there's a puff of HBr or HCl, depending on what kind of halide it is, because even the traces of moisture, and you can't avoid it in the process of packaging, it hydrolyzes a tiny amount, and that sits there in the atmosphere, and it blows out when you open the bottle. So this is hot, it's fast, and you don't even need a catalyst, although if you use a catalyst, that's fine too. In fact, acid is almost always present in any commercial acyl halide that you buy because a little bit is hydrolyzed. Okay? So HCl or HBr floats around. So with catalysis, it goes even faster, okay? But it's already fast enough. Anhydrides are much more well-behaved. They also react with water, but more slowly. And you don't need the catalyst, but with acid, it will go even faster. Okay? The reason that because they are so much better behaved, they are very popular in industry, okay? Because you have less safety precautions, less corrosion, and all that. Esters are quite stable. They occur in nature, they occur in our body, they're the flavoring agents of banana, apples, and lots of fruits. I mentioned this on Tuesday, I think. So they sit around with water. Actually, basically nothing happens on what one could call laboratory timescale, meaning months. Nothing will happen. But when you use acid or base catalysis, then you can hydrolyze them. So here with acid, that's the acid catalyzed hydrolysis of an ester. With base, it's hydroxide attacking directly additional donation to hydrolyze to the carboxylic acid in alcohol. In amides, they're rock stable, really. I'll call it exceedingly slow, but that definitely nothing will happen in your lifetime. Otherwise, your body would fall apart because as I mentioned before, your proteins, enzymes, polypeptides, they're all made of amide linkages. So you need a catalyst and you need typically prolonged heating to cleave amide bonds. In a biolab, when you do an amino acid assay of polypeptides, meaning that you hydrolyze the polypeptide at all the amide linkages to liberate all the component amino acids, it's typically done with free normal HCl at 100 degrees for several hours. Okay? So you need to heat on the system to get these things to hydrolyze. So what are the origins of these trends? You already know this, but let me summarize it. One is the inductive effects. Okay, as you move from right to left, you get less and less electron withdrawing, and so less and less reactive. That's why the amides are the least reactive, the halides are the most reactive. And related to that is resonance, namely the availability of this lone pair to enter into resonance. Okay? So for the generic acyl derivative with a leaving group that has an electron pair, you can write these resonance forms, and these are the two major ones, A and C. This is a sextet structure, but this one and that one. And that one is a contributor that involves the electron pair on L, which clearly stabilizes the carbonyl function. Okay? And so the ability to donate is clearly dependent on where in the periodic table you sit. And if you're more electron withdrawing, like this being a halide, this resonance form is rather minor. But if you go all the way to the right, where this is an amine, which is the least electron withdrawing atom, then the lone pair is the most available. This is why amines are basic, actually, in aqueous solution, the active bases. And so this resonance form becomes quite dominating. And I'm showing you two extreme electrostatic potential maps, one for acetyl chloride, where the chloride poles that this resonance form is rather minor. It's basically this, and this carbon is really blue. And here's acetamide, where now there's a strong contribution of this resonance form. And notice this carbon here is no longer blue. It's sort of greenish. It's starting to actually fade into yellowish, okay? So meaning much more electron density at that carbon, much less delta plus at that carbonyl carbon. So to organize this within the context of what you've discussed ad infinitum in chemistry 3a, so that's a nice reminder, from left to right, halogen, carboxylate, alkoxide, amine, decreasing electronegativity, right? Therefore also decreasing leaving group ability, because remember from chapter 6, the better leaving groups are the ones that can accommodate the negative charge that they're schlepping with them as they leave, right? The best. Decreasing acidity of the conjugate acid, meaning that the ability of L to accommodate the negative charge is related to acidity, obviously. The easier it is to dissociate means that the easier it is for the L minus to accommodate the negative charge, and therefore increasing contribution of resonance form C, meaning ability to donate an electron pair. These are all related to each other. They address four different phenomena, but they're all related to the same aspect. How happy is L with a negative charge, and or how easy is it for L to donate an electron pair to generate a resonance form that is shown up there. So these differences are reflected in pKa values also, of course. So the hotter the carbonyl, the more basic this oxygen. Okay? And so the ease of protonation increases as you go from right to left in our series of compounds, from left to right in our series of compounds, meaning that amides are best because the amine is most capable of setting up this resonance form, of donating this electron pair, kicking out this electron pair. So amides are most easily protonated, whereas acyl halides are the least easily protonated. All of them are not great bases, by the way. Okay, so this is all relative. For the same reason, deprotonation now gets more difficult, meaning that the hardest carbonyl with most delta plus is now the most acidic. And that's why acyl halides are actually more acidic than aldehydes and ketones. Okay? And if you remember, well, they're about as acidic as an alcohol. Okay? So if you remember 15 is a good number, then to go to aldehydes and ketones, it's a factor of 5, another factor of 5. It's an increment of 5 pK units. So that's a factor of 100,000. Right? And then from here to esters, it's another 25, another 5 up, so that's 25. And from here to amides, it's another 5. That's actually a good series to remember. Acyl halides, aldehydes, ketones, esters, amides, it goes up in increments of 5. And the acyl halides are about as acidic as water. Very roughly, plus minus a couple of pK units. But that's the kind of thing that is good to keep in mind when you think about relative reactivities. Okay, let's have a break. Okay, for intermission entertainment, we'll do another problem, a synthesis problem, which is also a typical problem that may show up in an exam where you are constricted to certain starting materials. That is to say, either you're asked to make something using only certain starting materials, or you're asked to make something definitely incorporating 2 starting materials and anything else. Okay? And so this is a case where we wanted to make this guy from incorporating these 2 starting materials in some way. And here now, because of the visual complexity, topical complexity of the molecules we're starting to deal with, you can't see how this unfolds from here just by staring at it. It's not possible. Okay? So you definitely have to resort to the mechanism of retrosynthetic analysis. You unravel the product in some way such that it's easier and easier to simplify it by chopping it up into pieces. And the smaller it gets, the easier it will be for you to see some kind of a connection between these pieces. So the second thing to do is to do a little bit of analysis. We have two carbon fragments that we can use. And this guy has 1, 2, 3, 4, 5 carbons. Okay, so somewhere along the line, we have to introduce an extra carbon if we use these 2 starting materials to make a 4-carbon piece. Somewhere along the line, we need another carbon. So it's not obvious how this will happen. If you start working blindly from here and here, it will be difficult, impossible, I would say. Well, maybe some of you are getting quite good at this, so maybe not totally impossible. But for most of you, this is not the way to go. The way to go is to simplify this. And this one way to simplify tremendously visually and operationally is to turn a cyclic structure into an acyclic structure. In this case, particularly advised because this is a cyclic ester. Okay, so we should retrosynthetically cleave it, at this function to generate the corresponding carboxylic acid, hydroxycarboxylic acid. That's what happens when you do that. And notice, just simply visually, that this now seems much more tractable than your starting cyclic system. Okay? This, you can already massage. There's a hydroxy, a lot of stuff you can do, precursors to this. There's a carboxylic acid, a lot of stuff you can do with respect to the carboxylic acid. In fact, staring this carboxylic acid